All right, hello everyone. Welcome back to video number 5 for regression analysis. This is going to be a video talking about the entire chapter number 4. All right, so 4.1 was our introduction. So in the past few videos, we spoke about simple and multiple linear regression models. When fitting a model to the data, we need to make sure that the fit is not being overpowered by one or a couple of observations. So distribution theory, confidence intervals, and hypothesis tests are only valid if the standard regression assumptions are satisfied. So we will discuss these assumptions momentarily, and serious errors can occur if the assumptions are violated. So moving into section 4.2, which is going to talk all about the standard regression assumptions. So properties of least squares estimators and statistical analysis procedures previously spoken about are based on the following assumptions. So the first assumption we have is the assumption about the form of the model. So the model relates the response variable y to the predictors x1, x2, all the way up to x sub p, which is the highest predictor that we have. So if we have 6 predictors, it'll go from x1 to x sub 6. So these are assumed to be linear regression with the parameters of beta sub 0 all the way up to our beta sub p value with the equation right here, y equals beta sub 0 plus beta sub 1 times x sub 1, all the way up to our beta sub p times our x sub p plus our epsilon value. So another way to write this is y sub I equals our beta sub 0 plus beta sub 1 times x sub I1, all the way up to our beta sub p times x sub ip plus our epsilon sub I value. So this is called the linearity assumption because it checks the assumption in simple linear regression. And in simple linear regression, it is easy to simply look at the scatter plot of y versus x. So if the scatter plot resembles a linear pattern, then we have linearity. Checking the linearity in multiple regression is somewhat difficult due to the high dimensions of data. So it is better to look at it in simple linear regression in this case, if possible. So graphs for this will be discussed a little bit later in this video. So if this assumption does not hold, transformation of the data can be done. So transformation of the data can be done to allow this assumption to hold. So again, we'll talk about this part later in this video. So the next assumption is going to be the assumption about the errors. So the errors are epsilon sub 1, epsilon sub 2, all the way up to our epsilon sub n. And they are assumed to be independent and identically distributed normal random variables with a mean of 0 and a variance of sigma squared. So we can imply 4 assumptions from this data. So our errors, epsilon sub I, are normally distributed. So that is referred to as the normality assumption, which is assessed by examining the graphs of the residuals. Also, the errors can have a mean of 0. The errors can also have the same unknown variance of sigma squared. So this is known as the constant variance assumption or homogeneity. So if this does not hold, then we would call this part heterogeneity. All right, and then the last part of the assumption of the errors is that the errors are independent, which this part is known as the independent error assumption. So the next assumption in the standard regression assumptions is the assumptions about the predictors. So as we know, our predictor variables are x sub 1 all the way up to x sub n, and they are non-random. So our x sub 1j, our x sub 2j, all the way up to our x sub nj are fixed, are selected in advance. So this is only satisfied when the predictor variables are set at predetermined levels. So this assumption is typically not satisfied for non-experimental or observational studies. So we would need an experimental study here to satisfy this assumption. Also, our x sub 1j all the way up to our x sub nj are measured without error. So this part is hardly ever satisfied because measurement errors are always bound to happen. And the measurement errors affect the residual variance, the multiple correlation coefficient, and the individual estimates of the regression coefficients. So correction for this requires knowledge of the ratio between variances of measurement error of the variables and the variance of the random error. So this is somewhat a little bit difficult to do, but with a lot of knowledge in this subject, it could be done. Predictor variables are also assumed to be linearly independent. So this is needed to guarantee the uniqueness of the least square solution. And when this is violated, we call that collinearity. And finally, our last assumption is the assumption about the observations. So observations are equally reliable and have an equal role in finding regression results. Small or minor violations do not invalidate conclusions, but we still wish to eliminate them. Right now, we're going to move on to section 4.3, which is going to discuss various types of residuals. So a simple method for detecting model deficiencies is to examine the residual plots. So we can detect possible missing info that might be overlooked. And a careful analysis of the residual plots may be the most important part of regression analysis. So we're going to obtain our fitted values from this equation right here in the top left, which is y sub I hat, which equals beta sub 0 hat plus beta sub 1 hat times x sub I1, all the way up to our beta sub p hat times our x sub ip. And this will have a corresponding ordinary least squares residuals of e sub I, which is equaling to y sub I minus y sub I hat. So the fitted values can also be written as this equation right here on the left on the middle using p's. So we can write that as y sub I hat, which is equal to p sub I1 times y sub 1, and adding up all the terms till we get to our highest term, which in general is represented by p sub in times y sub n. Where the p sub I, where the p sub i's are the quantities that depend solely on the values of the predictor variables. So we're not going to take into account the response variables here, solely the predictor variables. And to put this in terms of simple regression, we can do our p sub ij, which is equal to 1 over n plus, we're going to have a term here with the numerator of x sub I minus x bar times x sub j minus x bar. And then the denominator for this will be the summation of x sub I minus x bar all squared. So while in multiple regression, this p sub ij term is going to be the projection matrix. So when I equals j in the projection matrix, we have we can find p sub ii, which would be our term in simple regression. So our p sub I term is right here, which is equaling to 1 over n plus x sub I minus x bar squared all over the summation of x sub I minus x bar squared. So p sub I is equal to our leverage values. So n leverage values are denoted by p sub 1, 1, comma p sub 2, 2, all the way up to our p sub n values. So when these assumptions that we spoke about earlier hold true, the ordinary residuals will add to 0, but will not have the same variance due to the fact that our variance right here of the errors is equal to sigma squared times our 1 minus our pi value. So to overcome this issue, we standardize the values, and we can standardize using this formula up at the top here, which is equal to z sub I equaling to our e sub I value all over our sigma times the radical of 1 minus p sub I. So this is our ith standardized residual with a mean of 0 and a standard deviation of 1. And this is ideally what we want. So an unbiased estimate of sigma squared will be equal to this formula right here, which would be our sigma squared value times our summation of e sub I squared all over our degrees of freedom, which is n minus p minus 1. To break this down further, we can turn e sub I squared into y sub I minus y sub I hat squared. And then like we've seen in previous videos, this numerator right here is simply equal to our SSE value. And then of course we would divide that by our degrees of freedom once again. So this formula right here on the right is just an alternative way of writing out this formula. So we can do our sigma hat squared sub I, which is equal to our SSE sub I all over n minus 1 minus p minus 1. So to break that down further, we can take our SSE sub I value and divide that by our degrees of freedom of n minus p minus 2. So our SSE sub I value is the sum of squared residuals when we fit the model to n minus 1 observations while omitting the ith observation. So both of these are unbiased estimates of sigma squared using sigma hat to estimate sigma. So for that, we would get our r sub I. Now our r sub I is equal to our e sub I value that we seen earlier, dividing that by our sigma hat times the radical of 1 minus our p sub I value, which we also found earlier. So now if we would like to use sigma hat sub I to estimate sigma, we would use our r sub I star value. So for that, we would get e sub I in the numerator, and in the denominator, we would get our sigma hat value with the subscript of I times our radical 1 minus pii value. So r sub I is the internally studentized residual, and our r sub I star is the externally studentized residual. So externally studentized residuals have a t distribution with an n minus 2 minus p degrees of freedom. With a large sample, both have an approximately standard normal distribution. So they're related by this formula right down here at the bottom. So we can say that r sub I star is equal to our r sub I value times the radical of our degrees of freedom in the numerator this time of n minus p minus 2. And then the denominator in this case would be n minus p minus 1. And then we're also going to subtract our r sub I squared value. All right, so now we're going to move on to section 4.4, which is some graphical methods. So it is very important to use graphs to fit linear models to data. It is very easy to tell if a linear model fits the data simply by looking at the model. So it is also easy to use models to see if there are any outliers in a data set. So observations with a great influence on regression results are going to be called influential observations. And if you take a look at the list on the left here, we're going to have a list of reasons why graphical methods are very useful. So we can detect errors, recognize patterns, explore relationships, discover new phenomena, which is pretty cool, confirm and negate assumptions, assess the adequacy of a fitted model, suggest some things we might need to change in the study, or can suggest enhancement of numerical analysis. So this list on the right here are our two types of graphs. So we have graphs before fitting a model, which is useful for correcting errors in data and in selecting a model. And our second type, which is after fitting a model, which is useful for checking assumptions and assessing goodness of fit. So section 4.5 is going to talk all about the first type of graph, which is the graphs before fitting a model. So in this case, we have four possible groups of graphs. The first one is going to be our one-dimensional graph. So the purpose is to have a general idea about the distribution of each individual variable. So some examples of one-dimensional graphs are histograms, stem and leaf, dot plots, and box plots. So these are used to indicate the distribution of a particular variable and whether the variable is symmetric or skewed. If we do have a skewed variable, we should transform the data to eliminate the skewedness. Also, we can indicate outliers in the variables. So the second group of graphs is our two-dimensional graphs. So this is used when we have a set of multi-dimensional data. So only when we have a small number of variables, we can arrange up the pairwise scatter plots in a matrix format. Right. So we can also indicate correlation coefficients in the appropriate scatter plots. So in simple linear regression, a plot of y versus x is expected to show a linear pattern. But in multiple linear regression, we will have a scatter plot of y against each of the predictor variables, which may or may not yield a linear pattern. So the next group of graph is called a rotating plot. So plotting of three or more dimensions is going to use a rotating plot. And the only way we can really create this is by using computer software, since it is more than 2 dimensions. And by this, we can use a computer to play around with the plot and rotate the plot so we can see the whole data set. And then from there, we would be able to make conclusions and see outliers and influential observations and all that kind of stuff. So our fourth group of graphs is called dynamic graphs. So this is used to explore multivariate data. And this type of graph is also going to need computer software to create it. All right, so the next section is going to talk about the other type of graphs, which are graphs after fitting a model. So this is used to check assumptions and assess the adequacy of the fit. So this is grouped into the following classes, as you can see on the PowerPoint. So the first class is going to be graphs for checking the linearity and normality assumptions. The next group is going to be the graphs for detecting our outliers and influential observations. And then finally, our last group is going to be diagnostic plots of the effects of the variables. So these are going to be really useful in really getting a good feel of what the data is showing, so we can make accurate assumptions and conclusions based off of the data. And if we need to somehow retest, we can based off of these graphs. All right, so section 4.7 is going to talk about checking linearity and normality assumptions. So checking linearity when the variables are small is simple by simply manipulating the plots. So it becomes difficult when we have a lot of variables. The following can be used to check the linearity and normality assumptions. So the first one would be the normal probability plot of the standardized residuals. So this would be a plot of ordered standardized residuals versus a plot of normal scores. So this plot should resemble a nearly straight line with an intercept of 0 and the slope of 1 under the normality assumption. The second is our scatter plot of standardized residuals against each of the predictor variables. So our standardized residuals are uncorrelated with each of the predictor variables. So this should yield a plot of a random scatter points. And if a pattern can be seen, then a violation may have occurred. So in this part, we do not want to see a correlation. We just want to see a bunch of random points on the screen. The next part is the scatter plot of the standardized residuals against the fitted values. So this plot should yield a random scatter of points as well, as the standard residuals are uncorrelated. And then our last one is the index plot of the standardized residuals. So this displays standardized residuals versus the observation number. So a plot is only needed if the order is important. So points should be scattered randomly within a horizontal band around 0. So we wouldn't really use this one too much. The only reason why we would really need to use this if the order of our data is extremely important. Right, so we're going to move on to section 4.8, which is going to talk about leverage, influence, and our outliers. So we need to make sure that the fit is not overly determined by one or a few observations. So this is not possible to detect with several variables. So we do need one variable in order to detect these things. So just a little definition here. An influential point is when deleting the point will cause substantial changes in the fitted model. So we just need to keep that definition in mind when we are talking about this section. So when we look in the textbook with the example of the rivers in New York, it is extremely important to detect influential points. So these influential points are usually outliers in the response variable or predictor variable. So that example in the book showed the graphs when deleting one of the rivers, and then they showed like each graph with one of the rivers deleted, and we can see how drastic of a change each of them was. So that's a good graphical example to look at for this section. All right, so our first type of outlier are outliers in response variables. So these are observations with large standardized residuals. So an outlier is a point with standardized residuals larger than 2 or 3 standard deviations away from the mean. So that's how we're going to normally determine an outlier. So in this case, patterns are more important than the numerical values, since we can use the patterns to detect an outlier, and then we can translate that into our numerical values. So our outliers in predictors, which we have our leverage values of P sub II, which we spoke about earlier, which can be used to measure out the lyingness in the X space. So this is true for both simple and multiple linear regression. So these outliers are referred to high leverage points in order to distinguish them from outliers in the response variable. So these values lie between 0 and 1 with an average value of P plus 1 over N. So points with high leverage should be further examined to determine if they are influential points or not. So our final thing here is going to be masking and swamping problems. So these are analyses based solely on residuals that may fail to detect outliers in influential points due to the fact that the presence of high leverage points, which is our P sub II plus our E sub I squared over our SSE value, which must be less than or equal to 0. So this here indicates high leverage points that tend to have small residuals. So if a point does tend to have a small residual, then we should further look at it to see if it is indeed a high leverage point. So masking and swamping. So masking occurs when the data contains outliers, but we fail to detect them. So this would indicate that we had a false negative in the data or in observing the data. And then swamping, on the other hand, occurs when we wrongly declare some of the non-outlying points as outliers. So this can be referred to as a false positive when we observe the data. So our next section here is going to be section 4.9, which is measures of influence. So this is measured by the effect that it produces when it is omitted from the data. So that's how we can determine how influential a point is. So we're looking right here at the top left of beta sub 0 I hat all the way up to our beta sub P hat sub I. And this right here is our regression coefficients obtained when the ith observation is deleted. And also our y sub 1 sub I hat all the way up to our y sub n sub I hat. There we go. And our sigma hat squared sub I values are, these y values are their predicted values, and our sigma term right here is going to be the residual mean square. Both of these are going to occur when we drop the ith observation. And then this formula right here in the center is our fitted value for m when the fitted equation is obtained with the ith observation deleted. So all of these are going to determine if a measure is influential by determining when we delete the observation if it has a drastic change on the data. So our first measure we're going to talk about is Cook's distance. So Cook's distance measures the difference between the regression coefficients obtained from the full data and the regression coefficients obtained from by deleting the ith observation. So the way we find Cook's distance is we indicate it by our C sub I, which is equal to the summation from j equals 1 to n of y sub j hat minus y sub j I hat all squared. And we're going to divide that by our sigma hat squared times our p plus 1. And then another way right here to indicate Cook's distance is alternatively by doing, we indicate that by C sub I as well. And then we can have our R sub I squared value that we found earlier, divide that by P plus 1, and then we're going to multiply that term by a second term, which it consists of our P sub I value divided by 1 minus our P sub I value. So if we have a large Cook value, then that can determine that the point is indeed influential. So if we look at all the Cook values on the graph, we can use that to determine which point, if any of the points, are influential. So the next measure we have here is called Welsh and Cook measure. So this is going to be denoted by something called d fits sub I. So our d fits sub I is going to be found by doing our y sub I hat minus y sub I hat all over our sigma hat sub I times our radical with our p sub I value from earlier. And this is the scaled difference between the ith fitted value from the full data and the ith fitted value from the deleted ith observation. So just like we had an alternative method for Cook's distance, we have an alternative formula for the Welsh and Cook measure as well, which is simply our R sub I star value times the radical of our P sub I over our 1 minus P sub I value. So we can correspond this measure to our Cook's distance by taking the radical of our Cook's distance with the normalized sigma hat sub I value. So we can determine that an influential point is indeed influential if this the absolute value of our d fits number is greater than 2 times the radical of p sub p plus 1 over n minus p minus 1. So our Cook distance and our Welsh and Cook measure yield us very, very similar answers and can be used in the same way to determine an influential point. So one more measure we have is called the Hattie's influence measure, and that can be denoted by h sub I, which we're going to find that by having our p sub I value, dividing that by 1 minus our p sub I again, and then we're going to add that to p plus 1 over our 1 minus p sub I times our d sub I squared over our 1 minus d sub I squared again, where our d sub I is equal to our e sub I value divided by the radical of our SSE value that we know how to find from earlier videos. So this is called the normalized residual, which can be used for an overall general measure of influence, which shows observations that are influential on at least one regression result. So all these are really useful ways in helping us to determine if a point is indeed an influential point. All right, so now we're going to move on to section 4.10, which is the potential residual plot. So the graph of Hattie's influence measure is called the potential residual plot, since it is a scatter plot of the potential function versus the residual function. So the main usefulness of the potential residual plot is to find leverage and influence measures that gives a full picture of all the points in the fitted process. So this is really useful to see the model after fitting. Right? So now moving on to section 4.11 is we're going to talk about what to do with our outliers. So outliers and influential observations should not be deleted from the data since they are not necessarily bad. So if you have an outlier, don't go back to your data set and just delete it because it doesn't look like it fits. It needs to be there. So in fact, they can be the most informative observations in the data set. And corrective actions can be taken to correct an outlier. And some of those corrective actions are displayed on the screen right here, which can be correction of errors. We can delete or downweigh the outliers, transform the data. We can consider a different model. We can also redesign the experiment, or we can go back to the drawing board and collect more data. All right, so moving on to section 4.12. Our t-test should be in 4.12, which is the role of variables in a regression equation. So our t-test should be interpreted along with the appropriate graphs in order to determine if the variable should be retained or omitted. So two graphs that can be used for this is the added variable plot and the residual plus component plot. So our added variable plot allows for a graph to see the magnitude of the regression coefficient of the new variable that is being considered. So the added variable plot for x sub j is the scatter plot of is the scatter plot of the y residuals against the x sub j residuals. And now for our residual plus component plot, this is going to be used in the same way that the added variable plot is going to be used, except it's going to be a scatter plot of our e plus beta sub j hat times our x sub j value against our x sub j residuals. So E here is the ordinary least squares residuals when y is regressed on a predictor variable. And our b sub j hat is the coefficient of x sub j in the regression. So this is more sensitive in detecting nonlinearity in the variable that you are looking to add. So both of these are good scatter plots to use to determine if a variable you are trying to add to your data set is in fact going to be influential or not. So now we're going to move on to section 4.13, which is the effects of an additional predictor. So when a new variable is introduced into a regression equation, we have 4 different possibilities that can result. Our first possibility can be that the new variable has an insignificant regression coefficient and that the remaining regression coefficients do not have much of a change. So new variables with this effect should not be included. Our next possibility is when the new variable does have a significant regression coefficient and that the previous variables are changed in a substantial way. So in this case, the variable should be retained, but collinearity needs to be examined before adding the variable to the data set. Our next possibility is that the new variable has a significant regression coefficient, but previous variables are not changed. So in this case, our new variable should be included in the data set. And lastly, our new variable has an insignificant regression coefficient. So previous variables are substantially changed. So in this case, we need to test collinearity before deciding if we want to add the new variable or not. So all of these are possible outcomes that can be seen when trying to determine if a new variable should indeed be added to the data set. Alrighty, and lastly, we're going to move on to section 4.14, which is robust regression. So this is a method of fitting which gives less weight to points with high leverage. So this is just a little intro to this topic. So this topic is going to be discussed further in future chapters. All right, so thank you guys for making it to the end. I know this video was kind of long, but just to wrap it up quickly, in chapter 4, we discussed our standard regression assumptions, types of residuals, our various graphing methods, what to do with outliers, and how to determine if a point is an outlier, an influential point, or has high leverage. And we went over our different measures of influence. So thank you guys again for watching, and I will see you next week.